Yeah, let's continue our journey to this counting problem. So today we are aiming to broaden our setting to some more bizarre or more interesting examples. But so just recall, I will not go through all these 3 steps. It was quite involved, and it's not something that can be summarized within 2 minutes or something. But we first established that this limit exists. I never gave you the correct naming. I never wrote it down. I'm sorry. This is sometimes called the volume entropy. Yeah. So if your action is co-compact, then it's more or less the volume entropy. So volume entropy is a priori should be defined differently, but if you're having co-compact action, then. But the more appropriate naming will be the critical exponent. This is the critical exponent of G, but associated with the group action. So, and I told you last time, the existence of this limit is telling that this function, the population of bullet radius R is somewhat exponential, similar to exponential function up to discrepancy of sub-exponential function. We obtained much more precise estimate. That was step 2. So there were 2 parts, the lower bound and upper bound. Lower bound was followed from the Fekkatas lemma. Upper bound, we had to construct a map that has some injectivity to ensure this kind of property. So we aim for this equality, which almost hold, for example, for free groups, but in general, it's not the case. What's relevant for the upper bound was this direction. But it was not it cannot hold as is. You should embrace some constant, but that's observed by this K1, so it's fine. And finally, we related the geodesic between orbit points to the conjugate classes. So it was more or less linear to 1 map. It was via linear to 1 map to establish the upper bound, and also we observed the lower bound. So this was for co-compact. So yesterday, it was for co-compact action on delta hyperbolic space. And whenever we constructed some maps, the important picture was like this. So today, I'm not gonna write down probably the exact formulas letters or something. Today, I just want to lead you to what I'm gonna talk about next week. So it'll be a bit more open-ended, but I just want to deliver some core ingredients and message from the theory. So what was the core ingredient? So just remember this configuration. So if you have so group is acting on the metric space. So let's say you had 1 progress by a group element, and probably you will also have another further progresses by different elements. But you can always make intermediate progress by one of the by this FIs where these are chosen from your favorite set. There was square, phi psi, psi phi, psi square. Actually, the correct formula for this set is really irrelevant. It's just that FIs are coming from lots of independent Luxdormics, but not terribly many. You can just do it between 4 independent elements. But what's the property that you require? the local alignment. So Fi is really not canceling out the progress made by G1, which like if I reinterpret, it does not erase the information recorded by G1, and it makes further progress. And also it does not cancel out the beginning progress by G2. So you can secure local alignment here, as well as here, and so on, so stepwise. But the magic of delta hyperbolicity was then, like if you can do that stepwise at each step, then you get the global alignment. That means these points are actually forming almost geodesy that are like uniformly not that far from the eventual geodesy. Okay, so today I also prepared you the picture. You can pick either 3 of these examples. So the first one, this is something related to the Z square free product. Just to make sure, I just brought F2, but it could be just Z. So let's give it a name. This is A, B, and free product, let's say CD. So this is generated by 4 generators, but the only relation is the commutator relation between A and B. So this is the question of the universe, some simply connected space that this group acts on, and this is the question. So probably this is the direction of, okay. I will draw like this. This is A, and this is B, and these are C and D. Okay, so this is G, and this is not X. This is X quotient by G. So X is something else. What is this? You first unwrap this torus, so you will see a flat, but you will not see only one flat. It will be everywhere. How do you move around different stories? Via the progress made by C and D. So whenever you draw some edge corresponding to C or D, then you will see different flats. So some people call this like a tree of flats. Yeah, I can see the tree. Okay, so just to let you know, this is a nice space. Why is it? First, this looks like a K0 space, and this is probably a K0 cube complex. I'll ask Indira later. But this is a K0 cube complex. But this have like unbounded like flats. So this is perhaps for example, not a delta hyperbolic space because you have two large flats. This is okay. Why did I brought up this example? So if you do not want to deal with this one-dimensional progress, like the mixture of one-dimensional and two-dimensional parts, if you want some so this is too much like tree-like. So probably this is due to like tree-like behavior. If you're braver, then you can also bring this example, which is question of this space, pi1 sigma, and there's also pi1 torus. That this is sigma, this is torus, and you just amalgamate along two just infinite order elements. I will not write it down. This is just X is something else. So you will have the unwrapped version of sigma, the universal cover of sigma, and you will also have different parts of different copies of universal cover of sigma that's interviewed by this flats. So the reason I brought this example is still this universal cover has too many flats, but it also have some very hyperbolic-ish part as well. The final example is something different. This is a question of delta hyperbolic space. This is just a puncture surface. So G is pi1 of sigma, let's say G, but with two punctures. So what's the point of this example? This is not co-compact like anymore. So X is like space. Okay. So you question out X, but not in a co-compact sense. So the fundamental domain will be something like this. All right, this is not the correct picture. Just, yeah. But it has some cusps. So just let's keep these in mind, and let's try to go through this like 3 steps. Okay, first, it's a co-compact action, like for the first 2 examples. Sorry. Today, co-compact action on a Cat0 space. But with some hyperbolicity. So what is the hyperbolicity that I require? It's that I want some rank 1 isometries. So what are these? I will define it. So Cat0 space, so if you have a simply connected Cat0 space, and if you have an isometry, G, then there are 2 choices, 2 possibilities. First, if you investigate how far just a point in X moved by G. So if you ask if there exists a point X such that the displacement is actually realizing the infimum of the displacement made by this isometry, for all, like you just probe through all possible points on the space. Is there one that achieves the infimum? No, then you call it a parabolic. G is parabolic. Yes, then you call G semi-simple. And there are 2 cases. So for semi-simple case, either the infimum is 0. This means the point that achieves the infimum is actually fixed, and you call G elliptic. And if the infimum is actually positive, then you see a positive like translation, just as you see non-trivial translation on the Euclidean plane, and you call G loxodromic. So for example of loxodromics, so if you have a Euclidean plane, and if you have a non-trivial translation, then this is loxodromic. But in this case, you cannot pinpoint where the axis, like sort of like the axis is that you expect in hyperbolic geometry, because every point qualifies as the optimal point. But recall that hyperbolic plane is also a Cat zero space because the triangles are not that thick. And if you bring non-trivial logarithmics, then the points that achieve the infimum is along a single geodesy. And why is this the case? Because if you're off that geodesy, so if the infimum like set was not a geodesy, then this point and this point are having like the same infimal like displacement, but the quadrilateral that you draw and you take the midpoint, then there's some kind of like contraction, right? So this will be moved for a smaller displacement, which is the contradiction. So basically, this is related to the fact that whatever quadrilateral you draw, that's not quite flat. It has some hyperbolicity, so it should be like shrunken a bit, like the sides are like pulled together. So I'll not prove anything, but I will just use this as definition. This might not be a standard definition, but it should be equivalent to the standard one. So on isometry, G of, for now, let's assume properness of the space as always. So proper Cat zero space is called rank 1 if it has an invariant geodesy that does not bound any flat half plane. So, for example, any logarithmics in hyperbolic plane are called rank 1. Please. Mm-hmm. Right. Right. So I think at least in this realm, like for proper Cat zero space, that's precisely correct. That the invariant set, this infimal set might not be actually a single geodesy. It could be like a strip. So it could be a product of a geodesy and some other like geometric shape. But if that's bounded, then it means that you cannot go further like with really parallel like transport like for arbitrary like distance. That tells you that you cannot have this geodesy cannot bound a flat half plane. So that's pretty much the equivalent way to say this. Okay. And there's a, oh yeah, please. Mm-hmm. Uh-huh.
We act by translation. We also rotate the half class.
Uh-huh.
Then it seems like the space of geodesics is just a single line.
Right.
So like there's no
Then right. Then is it rank 1? No, I'm excluding that case. So this is not meaning that your infinite set is like geodesic times finite diameter. It's stronger than that. So like in the example that you mentioned, like the infinite set is really like setwise just a geodesic, but it bounds tons of infinite like flat half space, but it just rotates, right? But in this case, I exclude that kind of cases. So for this study, I brought up this notion. First, question, do many group actions on Cat0 space involve rank 1 isometries? Well, I have two answers. At least for Cat-1's case, or like if your Cat0 space happens to be delta hyperbolic as well, then we have fairly good understanding of the possible dynamics that you can have. I mean, there are always the degenerate cases that you should, and they can also entail some like interesting dynamics, but for most cases that arise in geometric group theory, if your action is non-elementary, then it has two independent loxodromics at least, which means, and if your Cat0 space happens to be delta hyperbolic space, and if you have a loxodromic, that's rank 1. So for Gromov hyperbolic Cat0 space, it depends on the way you define many, but to me, it's many, so yes. And also, another example is, again, I'm not taking any responsibility, but for any, like, if you have any questions regarding Cat0 cube complex, there are many experts here, so please ask them. So for Cat0 cube complexes, so if you know that the group is co-compactly acting on Cat0 cube complexes, there's a fairly good understanding due to Kapras and Sagiv. Namely, if your action is somewhat irreducible, what does it mean? It does not split into the products, then you're bound to have tons of rank 1 isometries in that group action. Okay, and second, why is it useful? Why does it come into our study? Another definition. A geodesic gamma in a metric space is called, sometimes strongly, but some other authors call it just without this adjective. We call it strongly contracting or just contracting if verbally, just with plain English, if the metric poles disjoint from gamma has uniformly bounded projection onto gamma. Again, the picture is, this is again H2. You pick any geodesic. Now, there are a bunch of metric balls. So you can draw it here. You can draw it here. you can probably do this kind of very large ball, or yeah, okay. So among these, this and this are not qualifying for my to plug in my definition because they are not disjoint from the gamma. So don't bring these. These are irrelevant. What I care are metric balls, something like this. You can draw it like arbitrarily large. That's true. I mean, there are plenty of room in the half space, so you can draw it as large as you want. But that doesn't matter because, however, what's the largest ball that you can plug in? I mean, if you allow it to touch the boundary as well, then it should be something like the ball that's tangent to both gamma and tangent to the boundary at a point. This is more or less unique. So unique up to the translation along gamma. The fact that it's unique means that unless this ball itself has unbounded projection on the gamma, this will be the upper bound to the diameter of the shadow that we will see. And this indeed has uniformly bounded diameter of projections. So for hyperbolic plane, I think 100 works. Okay, this you can blame me. Like I should have done the calculation. Yeah, 100 works. 2 square root of 2, yeah, probably it might work. Yeah, so it's definitely 100 should work. Yeah. This is how I passed my qualifying exam. Yeah. Okay, so this is smaller than the size of this largest possible shadow is smaller than 100. So any geodesic in H2. And more generally, if your space is delta hyperbolic, then you can show that any geodesic you pick in that space is strongly contracting. And okay, this constant is associated to gamma. So sometimes you attach the parameter like k strongly contracting if the bound is like k. Can you set k to be uniform for any geodesic in a delta hyperbolic space? Yes. So this k can be computed explicitly from delta. And also, so I defined rank 1 isometries like so, but let's do some cheating. This is a property enjoyed by this geodesic, so I will call this property also as rank 1. So a geodesic in a K0 space is rank 1 if it does not bound a flat, flat half plane. So you can anticipate that any rank 1 geodesic in a K0 space is also strongly contracting. That's almost true, except the cheating that suppose that you have. So this is just a line. You just attach a small square, some larger square, some more larger square, and so on and so on. Why do I do this? This is all finite, so I cannot attach like an infinite flat plane to this geodesic. So this is rank 1, but like you have arbitrary root, like you can draw arbitrarily large ball that projects just perpendicularly with respect to Euclidean metric, which is a cheating. So to prevent this, how can I show this? What kind of condition can I impose? Any geodesic, so any rank 1 geodesic, that is invariant by invariant under some translation along. So basically, I'm making this gamma to be periodic under the action of G, such that you cannot like do this kind of cheating, because if you have plugged in like this kind of small square, then it should appear forever. Like you cannot plug in arbitrary like large square afterwards. So is strongly contracting. So basically, okay, in short, the axis of rank 1 isometries, they are all strongly contracting. Of course, Nicholas pointed out that like there could be no like unique invariant geodesics, so there could be several. So okay, what do you mean by axis? Okay, it's a union of those geodesics, but any of these geodesics will be strongly contracting. Any questions so far? Okay, so this is some sort of like reformulation of rank 1 geodesic that I like tried to define there. Why is it useful? So advantage or like its usefulness. In one plain language, strongly contracting geodesic enables us to execute all the strategy that I mentioned in bullet 1, 2, and 3. So that is the point of today's lecture. So I can write like this. We can promote the local alignment among contracting geodesics into the global alignment. To be precise, I'll draw a schematics. So here are 3 strongly contracting geodesics. Then, and I assume that this geodesic is not canceling out the direction that's made by gamma 2. How can I say this? You project gamma 1 onto gamma 2. You take the nearest point projection. If gamma 1 was like along here, then for this point, it will project down to gamma, like some middle point of gamma 2. But I will prevent that from happening. So that's my requirement. So the requirement is gamma 1 is projecting onto somewhere nearby the beginning point of gamma 2. And gamma 3 is also not canceling out. Like it's not also going like against gamma 2, but it just peacefully projects onto gamma 2 nearby, near the ending point. So requirement gamma I plus 1 are aligned. And by alignment, I mean gamma 1 is projecting like onto gamma 2, like near the beginning point of gamma 2. Gamma 2 is projecting onto gamma 1 near the ending point of gamma 1, and so on. And what I want is consequence is gamma I and gamma J are aligned. What do I mean? So gamma 1 and gamma 3 are now far away. And a priori, I haven't like imposed any conditions between those 2 geodesics, but I will deduce that gamma 1 the projection of gamma 1 onto gamma 3 is close to the beginning point. So for example, gamma 1 could not be here. And the same goes to the gamma 3 from the viewpoint of gamma 1. The proof is not that hard. Observe. This is sometimes called bounded geodesic image property. So it has its own name, but some people also use it as the definition of contracting property. So it could be confusing, but I mean, they're really the same. So I'm going to state some property of strongly contracting geodesic. Observe that geodesics. So there it was metric balls, but this time geodesics far away from strongly contracting geodesic. Gamma, let's give them a name. This is eta, this is gamma. Cannot have a large projection onto gamma. So here's gamma. This is strongly contracting. If I know that this some random like geodesic somewhere else in the metric space, like if you take the nearest point projections, if the projection is larger than a uniform threshold, then this is observed. It should have been like this. So in some sense, you can say gamma is really bottlenecking. So like gamma, what does gamma actually do? So it has like every point like projects onto gamma. So it kind of like stratifies the entire space. Like just imagine in the hyperbolic plane, or the better example is here actually. So like you have this tree-like directions. This is just a geodesic in the entire metric space, but every point has its landing point onto this gamma. So this is how this strongly contracted geodesic is like dividing up the entire space. And if you belong to sufficiently distant stories, then the only way to get from here to here is to go through the geodesic, because this geodesic is really tree-like. And for a hyperbolic plane, you cannot really say that they really exactly go through the part of the strongly contracting geodesic, but it comes sufficiently close, uniformly close to the geodesic. So this is one observation, and assuming that if my gamma 1 and gamma 2 were here, and gamma 3 were here. Let's say this point is projecting somewhere here onto gamma 3 somewhere here, like not very close to the beginning point of gamma 3. Suppose to the contrary that this is like so. But I assume that the entire gamma 2 is like should enter gamma 3 like from the beginning point, right? So for example, if I pick this point, this is projecting onto here like this. And since we observe this, the geodesic between these 2 points should be like this, which is quite absurd because, so in particular, along its journey, this geodesic, so let's give them a name, X and Y, and this weird path is actually the geodesic between X and Y, and it goes through some point that's like in the middle of gamma 3. So and then this point, now this point, from the viewpoint of gamma 2, this and this project far away on gamma 2. as well. So actually this subsegment of X, Y, this passes through almost all of, this passes through almost all of gamma 2, right? Actually, the same goes for the beginning beginning subsegment as well. So basically, you're claiming that, so here's gamma 1, and here's gamma 2, and here's gamma 3. I mean, you're allowing some bounded amount of error, but you're basically claiming that here is some point that's far away from the beginning point, and then you're claiming that this is the geodesy. What does it mean? The length of the total path is not only almost the length from here to the ending point of gamma 1, but you have excess length as well. This is quite not the case for geodesics, hence the contradiction. Hence, any point on gamma 1 cannot have a projection that's sufficiently far from the projection of gamma 2 on gamma 3. The local alignment. So yeah, so here we assume that gamma 2 is projecting onto gamma 3 near the beginning point to secure the distance between the projection of X and the ending point for towards the contradiction. Is there any other question? Mm-hmm. Right. Right. Yeah. So as I pointed out, so the projection of gamma 1 and gamma 3 onto gamma 2 should be also sufficiently large so that you can deduce the contradiction from the axis length here. So this is this length is L1, and this distance, L2, which is almost equal to the distance of the gamma 1 and gamma 3 seen on gamma 2. This should be also sufficiently larger than the bounded amount of error, so that you deduce the contradiction that L1 should be the smallest, but this is smaller than L1 plus 2L2, and plus something else, but that doesn't really matter. If L2 is sufficiently large, then this is a contradiction. Okay, so I'm indeed quite lazy because this is not actually the configuration that I promised to you, because, okay, there's the reason for the colorings. Here, I only colored the progress made by F1 and F2. Why is the case? In case so let's try to utilize that property when you study counting problem on K0, group actions on K0 space. Let's try to do that. So what's the point? Not all geodesic progresses are contracting in this case. So you will not have this kind of local to global promotion between arbitrary geodesics on K0 space, right? You can have progress through flats. It could be, so for example, in the course of the argument, we pick G1 from just a bullet radius R. So inside there could be some group element that's progressing only through the flats, right? So G1 might not be strongly contracting in the argument. Okay, for F1, I chose that from my favorites. So if you pick that from just independent rank 1 isometries, you can ensure that these are strongly contracting. But G1, G2, G3, they are totally random. It could be flat, it could be rank 1, it could be the mixture of those two. Then how do you use that property? Okay, this is why I'm being lazy, because it's a, if I'm too lazy, I will leave it as exercise, but I'm not that brave. So in the discussion session, we can discuss it in full details, because next week I'm trying to convince you that you can push this to much like greater generality. So a remark is, in fact, in the rightmost configuration, I was hiding the fact that gamma 1, gamma 2, gamma 3 need not be contiguous, okay? So the point is, gamma 1, okay, you just barely require that gamma 1 and gamma 2, gamma 3, they have the correct like projections. So, and even you can recreate a point here. So the correct lemma you need is X is projecting onto gamma 1 to the beginning, gamma 2 is projecting onto gamma 1 to the ending, and so on and so on. So you have this nice projection, but locally. Then X is, for example, to the gamma 2, it's seen like near the beginning, and Y is seen near the ending. So actually you should embrace an arbitrary like progress between gamma 1 and gamma 2. The gap between gamma 1 and gamma 2, it could be flat, it could be rank 1, but I don't care. So that is the correct lemma that plays the role in the argument. But yeah, I will not go into this proof, but it's almost the same. So we can do that later. So the conclusion is need not be contiguous. And actually you can conclude that, we can conclude here that the geodesic from X to Y, so because you can prove that X and gamma 1 or X and gamma 2 and all these things are globally well aligned as well, what you can conclude is it has subsegments, fellow traveling, gamma i's. And in the correct order, what do I mean? It will have the first subsegment that is really nearby gamma 1, also matching the orientation. And after that, you will have the second subsegment. And finally, you will have the third subsegment. So for example, in the case, like in the example of like trees of flats, you can imagine that, I'll draw you the picture. So you can have lots of flats. And in reality, like when you're doing this argument, your G1 could be like the geodesic between the group element sending X0 to some other point in the same flat. Okay, that's not rank 1. So that's a bad news, isn't it? No, because then in the course of the argument, you will choose F1 to be deliberately through the C direction or D direction. That's a tree-like direction, right? So you will go to this direction, and you will require that, for example, the next G2 could be flat, or it could be like C times A or something. So it could begin with some tree-like direction, right? Then you should take extra care so that this rank 1 geodesic was not canceling out that direction. So that's our requirement for this configuration. But whatever that is, so I make another progress. It might go through different flats as well. So this is, let's say, G2. And then you connect them to the next progress via F2. And your final destination. G3. And what you get at the end is the geodesic between x0 to your destination, let's say this time y. The geodesic, okay, here you could detour actually. For flats, you're not forced to follow like one geodesic that you have chosen. You can have several geodesics that's far away from each other, connecting the same two endpoints. But at least while traveling along this tree-like direction, they are forced to be like exactly matching that tree-like direction. If your path is really efficient, namely geodesic. And also you can detour, and also here you might not detour, but here you might also detour, but at least during when you're passing through the progress by rank 1 geodesic, it's brought exactly close to the rank 1 progress. That is what this lemma or observation tells you, and that was the only thing we needed for the items. Is there any questions here? Okay. That's the geometry behind the argument. But here's another question. So is it cat-zero geometry or not? Somehow, because in order to get secure these rank 1 isometries, I use some results by Kaprasagiv and, for example, from study of delta space to secure this kind of rank 1 isometries. But is it really using cat-zero geometry? No, I haven't really. I haven't used the fact that, for example, the visual angle is well defined or somehow non-contraction property or something. I really didn't use it. I only used the contraction property of certain geodesics out of many geodesics in the space that's associated to some group elements. So how general does this strategy apply? And this is, in this generality, this is all due to Wen and Yang. So this is due to Wen and Yang. And also nowadays there's a fairly good complete theory of Patterson-Sullivan theory for this kind of group actions that I'll be mentioning. This is due to independently due to Yang, Wen and Yang, and also Rémy-Coulomb. But it's notable that the counting problems, and also for Yang observed that this kind of machinery works, and the application to the closed geodesic counting problem, it's due to Gechtman and Yang. So how general is this strategy? First, the mapping class group action on the Technion space also entails some contracting geodesics and contracting isometries. Namely, the thick geodesics in Technion space are strongly contracting. This is due to Minsky. And also, I mentioned that if the cat-zero space happens to be also the hyperbolic space, then there's rank 1 isometries. That's not so. In general, for hyperbolic spaces and namely hyperbolic groups, all loxodromics are rank 1 isometries. And like now let's forget about rank 1, like you're like escaping from cat-zero geometry. The isometries are strongly contracting. That means it's coarsely preserving a geodesic that is strongly contracting in the calligraph. And also you can plug in relatively hyperbolic groups. So for hyperbolic groups acting on any co-compact, like for any co-compact actions, for relative hyperbolic groups on their any calligraph. So if you have a relative hyperbolic group, you have a loxodromic element on this calligraph, and that coarsely preserves a strongly contracting geodesic in the graph. And some small cancellation groups as well. And also many right-angle arcing groups and groups with Garside structure. I'll not go through that, but if you're curious about braid groups, they have the structure. So if you want to count orbits or closed geodesics on these groups and group actions, you're welcome to use this machinery. Actually, that's the work of Wenyan Yang. But here's a question. These actions that I described on the calligraphs, or this is also on calligraphs, these are co-compact actions, but this is something else. This action is not co-compact. And if you recall the steps of the 3 steps, I used at least 2 points that the question has bounded diameter. Hence, you can find an orbit point that's close to the middle, like the intermediate point on the geodesic, wherever it is. I use that kind of fact. But for like mapping the action on time space, there's no such thing. So how will you cope with that? That's why I brought this example. I will mention the solution and then leave some questions and then finish. Okay. What about non-co-compact actions? So mostly the problem is like this. If you have, so while counting either geodesics or, while geodesics connecting 2 orbit points or the closed geodesics, you might be wrapping around very deep into the cusp, and then you will come back and something. And if you recall, this is seen on the universal cover, like this. This is corresponding to 1 orbit point, where you cannot chop it down into 2 intermediate progress, whose progress sums up, right? So if the action was co-compact, that was possible, but in this case, you will not find any orbit point that's nearby this point, because it had excursion through into the cusp. So the orbit points are probably you might find something nearby here and also nearby here, but in the middle, you have nothing. There's no orbit points. Or if you want more neat picture, I should have drawn like this, because this is how you draw cusps, right? This is the horocycle, and orbits are only here. But there are some orbit points that's approaching to this cuspidal point, and for this orbit points, you cannot reduce it to several intermediate steps. So how will you cope with that? So strategy or observation is that at least for this this group action, these group elements are quite distinct. Like, okay, it could be detected quite explicitly. Why? They are always associated to one of finitely many cusps, right? So there is a subgroup of this G that corresponds to the parabolic subgroup. So if you can just pinpoint the group elements from the parabolic subgroup, and if you can actually say that they don't matter, so they are quite negligible inside the entire group, then, like population-wise, then you can somehow ignore them and just proceed. So there is a notion of this critical exponent for the parabolic subgroup. So G has a parabolic subgroup. And this is, if this is smaller than, strictly smaller than the entire subgroup, entire ambient group, perhaps we can ignore the elements in P as if there were none. Okay. So this critical exponent basically tells you how large the population is inside the ball radius R, when it's comparably exponentially smaller than the actual population that you should count, then you might want to ignore them. Okay, this is not the proof. Actually, the proof is quite involved, but this is the strategy. So note or remark. For geometrically finite groups, Kleinian groups, or okay, I would say groups in rank 1 Lie groups. I mean, the action is on the symmetric space, okay? This is not a random negatively curved manifolds, but this is really symmetric case. One can show that HP is smaller than HG. And there are only finite many conjugate classes of these parabolic subgroups. Hence, you can actually execute this strategy. So this is due to, this observation is a combination of Corlett and EOT. They observed some feature of parabolic subgroups of geometric finite groups in rank 1 Lie groups. And actually, this inequality was showed in Dabo, Otal, and Peña. Okay, so if you're interested in portions of symmetric spaces, that's good. But we're in course setting. So what's the correct notion? In general, so these correspond to the case that you have a group element that's not inside a bounded neighborhood of the orbit set, but it's evading and it's going into an excursion away from the orbit set. So there's a way to just pin out those elements, and you can define some constant analogous to that. So this is let's say excursion. Let's write like this. I will not go into the definition, but if this is strictly smaller than the critical exponent of the ambient group, then we call it it has two names because it's defined by two independent teams. It's either called strongly positively recurrent, we abbreviate it as SPR, or it's either called statistically convex co-compact. So basically, if it were convex co-compact, what does it mean? Any geodesic that you draw between orbit points, it's within a bounded distance of orbit set, so you don't have to worry. But it is not the case, but statistically. So if you do it like in an asymptotic way, you can ignore those having excursion. So that's the reason. So it's either called SEC, statistically convex co-compact, if this holds. And I'll not give the proof, but the theorem by Gexman and Yang is that 1, 2, 3 works for SEC action. And this includes all these geometrically finite groups in rank 1 Lie groups and the action of mapping class group on the Technion space. The ingredient, this strict inequality for the action was observed by Eskin and Mizrahi. And the notion, this is due to Shapira and Samuel Tapi and Wenyan Yang. Okay, so I have 2 minutes. This is too much math. We should have some open end. So I will leave some questions that hopefully we can discuss. First, as I mentioned in the first lecture, still we have no idea how to deal with geometrically finite isometric group of generally like negatively curved, negatively curved manifolds. How? And second, so there was a question from the audience that can we actually make that as limit in the third item? So can we make like K1 prime and K2 prime as close to each other as possible? Okay, for course setting, it has not been achieved, but it's an interesting question. So in particular, related question is, so there's a, so in the course of the proof, we related the orbits and the closed geodesics. And we had to prove that the closed geodesics associated to each orbit points are non-degenerate. Like they actually goes to the actual closed geodesic, and it's kind of injective. The map is. So a related question is does every or almost every orbit point give rise to a non-degenerate closed geodesic? What do I mean? If you interpret this for a mapping class group, you might ask that is Sudanov generic in the mapping class group in the sense of counting. So in the sense of random walk, this is due to Rivin and Maurer independently. But for the counting setting, very limited knowledge is known. When you do this on the calligraph of mapping class group, So why is it difficult? I'll just mention one difficulty and then finish the lecture. Because basically we have no knowledge about the relationship between strongly contracting geodesics and the calligraph of mapping class group. So all this strategy was executed in many interesting groups, including right-angled arcing groups, some right-angled Coxeter groups, okay. But we still have lots of groups in geometric group theory that's not known to be related to the strongly contracting elements. And what's more, having a strongly contracting element is not QI invariant. So perhaps you might want some dynamics satisfy a group element that is also QI invariant, and that connects to this counting problem. So mapping class group has one candidate, namely the weakly contracting property of group elements that might lead to this resulting counting problem. I wanted to give you this news yesterday. I failed, but today I have posted one paper today on arXiv, but it should be more generalized. So we can discuss more on mapping class group in the next week. I'll finish here.
Questions?
Mm-hmm. Right. Right. So we have fairly good understanding in that in terms of geodesic and geodesic flow. So if you take a generic direction, then the excursion, the amount of total, the longest excursion till time t will be in the order of log t. So before you exceed time log t, consecutive time of log t inside cusp, you should come back. So we know that they come back quite frequently and quite early, quite not late. Oh, sorry, come again? So people have done this for hyperbolic groups. Yeah, that's true. Yeah, we also know that. Yeah, all of them. Yeah. This is, okay, there's a few more remarks. Actually, how do we know that this works for arbitrary calligraph of relatively hyperbolic group? That's via some other language. Basically, namely, relatively hyperbolic groups have non-trivial fluid boundary, and groups with non-trivial fluid boundary have strongly contracting elements. So that's a result by Pontakhalilu and Dresmov. Yeah. And there's a conjecture whether the class of relative hyperbolic groups and class of groups with non-trivial fluid boundary matches or not. We're not sure, but all relative hyperbolic groups have non-trivial fluid boundary.
Any other questions?
Right. So thanks to the question, I can explain a bit more about HAGs because so mapping class group, we're not sure whether any calligraph of the mapping class group, on any calligraph of a mapping class group, their pseudonce of is strongly contracting or not. We have no idea. But we know that on any calligraph, they are weakly contracting. I haven't defined it. It's basically metric balls that's slightly more farther away than being disjoint, have bounded projection. Okay, whatever. HHGs are known to have the same property. So all loxodromics on the top curve space have weakly contracting property on the calligraph of HHGs. That's due to Abbott and Burstock and Durham. Using that, you can conclude something about counting problem just as much as you can do for mapping class groups. But it's, for example, the question that I posed is not answered to mapping class group nor to the HEGs. So even braver, do we know that loxodromics are like loxodromics on the top, the hyperloop space is generic on asymmetric hyperloop group? That's widely open.
Any other questions? If not, then let us thank the speaker.
Okay.